Hey guys, in today's lesson we are going to talk about the differences between solutions or roots or zeros and what it means for something to be an x-intercept and what that means in terms of where in the number system, the complex number system, your solution lies. We're also going to learn how to write equations with complex solutions using the sum and product of roots, which we actually discussed yesterday. So starting right at the top, we're going to recall how to solve algebraically for each of the following equations. Okay, so starting with the first quadratic, first thing I'm thinking is, does this factor? Factors of negative 18 summed to negative 3 would be negative 6 and positive 3. So this actually does factor. And I get two solutions, 6 and negative 3. If I had to define where these numbers fell in the complex number system, I would say they're real and they're rational. And they're rational because I could express them as fractions of integers. Next, this is an x squared plus 16, so I cannot factor it like dots because it's, well, sots, I guess you could say. Because it's a sum. So what I'll do is subtract the 16. Take the square root, and I get two solutions, plus or minus 4i. And what you're noticing is I get two purely imaginary solutions. So I will list these as imaginary. Are they complex? Yes, every solution is complex, real or imaginary. So technically these are complex and they're imaginary. Lastly, over here, factors of 10 that sum to negative 6, 5 and 2, 1 and 10, none of those are going to work. So that means I need to either complete the square or do the quadratic formula. I'm going to complete the square to make things interesting. Subtract the 10 over, I should say. Put in my plus blanks. So half of negative 3 is, or negative 6 is negative 3, squared is 9. Okay, so I'm getting x minus 3 squared is equal to negative 1. I'll take the square root. Okay, so I get x minus 3 is equal to plus or minus I. So x is equal to 3 plus or minus I when I state that in a plus or minus bi form. Okay, so if I had to define these are also complex imaginary solutions. So I want to look at each of these. Specifically, these two I should say. Those are my complex solutions with imaginary components to them. What I'm noticing is I get a 0 plus 4i and 0 minus 4i. Over here, written separately, is 3 plus I, 3 minus I. When we look at these, they are almost exactly the same in their pairs, except they are off by a negative. So one is plus, one is minus. As we know from prior units, these are called conjugate pairs. So quadratic expressions with real coefficients have real or non-real solutions. This is what I showed you. The non-real complex solutions, so those are the ones with the imaginaries, always occur in conjugate pairs. So let's say you have a function and you know that 2i is a solution to that function. What that means then is that negative 2i must also be a solution because it's its conjugate pair. If you know 3 minus I is a solution to a polynomial, then 3 plus I must also be a solution. So again, it's extremely important that you guys know this fact. Sometimes I'll ask students, is it possible for a function to have 5 imaginary solutions? It is not possible for a function to have 5 imaginary solutions because every imaginary solution has to have a pair. I could have 2, 4, 6, or 8 imaginary solutions, but I can never have an odd number because they come in pairs. Now, I do have a slight typo here that I need to fix, just with some terminology that you guys will hear me using. When I say solutions, zeros, roots, those are all the same thing. They can be either real or, they should say, imaginary. Oopsies, imaginaire. Okay, so for example, if I get x equals 2, that is a solution, a root, a 0. And that's actually also an x-intercept because it's a real solution. It could be real or irrational, or excuse me, it could be rational or irrational, and it would count as one of those things. I could have 2 plus I. That is considered a solution, a 0, a root. But what 2 plus I, and I should really say 2 minus I, also would not be are x-intercepts. And that's because we discussed that imaginary solutions look like this. They don't touch the x-axis. They do not cross the x-axis. So what I'm trying to say here is that solutions, zeros, roots, these are all real or imaginary numbers. They are basically all your complex answers. But as soon as I talk specifically about x-intercepts, those have to be real. Okay, and that could be either rational or irrational. Okay, so coming on down, I've got a 4th degree polynomial, and I want to determine these solutions. So again, this is everything. This is your where it crosses the x-axis, where it doesn't cross the x-axis solutions. So first thing I can do is factor this to be x squared minus 4, x squared plus 1. Okay, and if I solve for 0 here, I would get x squared equals 4, so x equals plus or minus 2. X squared equals negative 1, which would mean x equals plus or minus I. Okay, so these are my solutions. My x-intercepts are the ones that only cross the x-axis. So the i's will not be crossing the x-axis. The 2's will. So when it says how many x-intercepts does this graph have, it has 2. Again, it's referring to the real ones. Now, if something is crossing the x-axis, that means that the y must be 0. So to give you a visual look down here, because I'll end up sketching it anyway, what I know about this function is that it has roots or x-intercepts at negative 2 and 2. And based on it being an even degree polynomial with a leading coefficient that's positive, I know my end behavior must look like that. Okay, so if I had to guess, the rest of this function probably looks something like this, kind of like a W. All right, and that's where the 4th degree comes from. So when I'm asking what are the coordinates of the x-intercepts, it's negative 2, 0, 2, 0. And that's what I meant by the y value must be 0. Okay, are the solutions to the polynomial function the same as the x-intercepts of the graph? Justify your reasoning and explain. No, the solutions are not the same as the x-intercepts. The x-intercepts are the only ones that specifically cross the x-axis. So I'm going to write here the solutions are plus or minus 2i. Oopsies, I'm sorry, not 2i. Plus or minus 2. And plus or minus I, but the x-intercepts are only the ones that cross the x-axis. So that would be plus or minus 2. So to put it another way, all x-intercepts are solutions, but not all solutions are x-intercepts. Okay, so now building upon what we discussed yesterday, we're going to write a polynomial in the lowest possible degree that has the following roots. We will use the sum and product to help us build these quadratics when needed. Okay, so starting with A, I'm noticing I have 2 real and rational solutions, negative 2 and 3. So those are where we're crossing the x-axis. And then I have 2 imaginary solutions, negative 4i and positive 4i. Notice how those are stated in conjugate pairs already for me, which is kind of nice. Okay, so you got to kind of think backwards here. If I have a root of negative 2, that would mean a factor would be x plus 2. If I have a root of 3, a factor will be x minus 3. And that's stuff we've been talking about since, I don't know, like Unit 1, okay? And then with these two, this is where I'm going to build the quadratic like I did yesterday by using the sum and product of those roots. So if I were to add negative 4i and 4i together, they would cancel each other out and go to 0. Now if I do negative 4i times positive 4i, I would get negative 16i squared. As we know, I squared is negative 1, so the product is actually 16. Yesterday we said we could write a quadratic by doing x squared minus the sum times x plus the product. So this is specifically a quadratic with a leading coefficient of 1. So I'll just fill in the sum and the product, which I can simplify to x squared plus 16. Alright, so these are the factors that I will put together to write my function. So p of x will equal x plus 2 times x minus 3 times x squared plus 16. Now in this example, just for good practice, I'm going to say, can you express your answer in standard form? So that means I'm going to have to distribute this all out to expand it, and then put it from highest power to lowest power. So first thing I would do is these two binomials right here, which is x squared plus 2x minus 3x is minus 1x minus 6. Okay, and I'll take that and multiply it by x squared plus 16. So I'm doing this. So I've got x squared, so x to the 4th, minus x cubed, minus 6x squared. And then I'll distribute the 16 going back. Okay, and then I just got to combine my like terms. So it looks like I just have x squareds to combine. Okay, and that's that. So coming on down to B, the rest of them I'm not going to put in standard form just to pick up a little pace here. Notice I give you a real root of negative 1 and then an imaginary solution of 3i, but remember imaginary always come in conjugate pairs. So negative 3i, you have to know, is also a solution. Okay. A factor that would give me negative 1 as a root is x plus 1. And as far as the imaginaries go, I'm going to do the sum and product. So similar to the one above it, sum would be 0. Product would be negative 9i squared, which would then be a positive 9. So x squared plus 9 would be the factor that gives me those solutions of plus or minus 3i, because I did x squared minus the sum plus the product. So putting it all together, p of x would be x plus 1 times x squared plus 9. Okay, next, a factor that would give me a root of 0, sometimes this trips you guys up, is just x. X will give you a root of 0. X minus 2 would give you a root of 2. Here are my conjugate pairs. Sum would be, okay, so I have 1 plus I plus 1 minus I. I's would drop out, so I'd get 2. And the product, since these are conjugates, we know we only really need to calculate the first and the last terms. So 1 minus I squared. Now remember, you're subtracting a negative 1, which would then go to positive 2. So then when I put it all together, this is x squared minus 2x plus 2 as the quadratic that would give me 1 plus I, 1 minus I as my solutions. So putting it all back together, my polynomial is x times x minus 2 times x squared minus 2x plus 2. Okay, last couple on this page. Something I want you guys to see here. These are irrational roots because they're radical 2's. Technically, those also come in conjugate pairs. So the sum of those would be 0, because they're exact opposites of each other. The product would be negative radical 4, which is negative 2. So x squared minus 0x plus a negative 2 would just be x squared minus 2. Okay? And guys, this makes sense because if you were actually to solve this, like set it equal to 0, wouldn't you add the 2 and take the square root and such? So that's why it makes sense that this quadratic is giving you those solutions. Okay? Sneak it right in there. 3 is one of your real solutions, one of your x-intercepts. So x minus 3 would be your factor. And then here we are again. 1 plus 2i is a solution, which means 1 minus 2i is also going to be a solution. Notice how I'm using the word solution and not x-intercept, okay? Because these are not going to cross the x-axis. Okay, so I'll do the sum, which the 2i's would cancel each other out, so I just have 1 plus 1, which is 2. Okay, the product I'll actually do out. So I get 1 minus 4i squared, which is 1 minus a negative 4, which is 5. So x squared minus 2x plus 5 would be the quadratic that gives me those imaginary solutions. Okay, so again, putting it all together, I just need to multiply these all together, and that will give me the polynomial. Okay, there you go. All right, one last one. Okay, solely imaginary solutions here. So again, I'm deliberately omitting some information here. I want to make sure you know that if 2i is a solution, negative 2i is also a solution. If 3 minus i is a solution, 3 plus i is also a solution. Okay, so sum is 0. Product would be negative 4i squared, which is a positive 4. So that means x squared plus 4 would be my quadratic that gives me those solutions. Okay, over here the sum would be 6, because the i's would cancel out. Product, 3 plus I, 3 minus I, is 9 minus I squared, which is 9 minus a negative 1, which then goes to plus 1, which is 10. So x squared minus 6x plus 10, because it's minus the sum times x plus the product, would give you the solutions of 3 minus I and 3 plus I. So putting it all together, p of x is equal to the product of those. So again, all I'm doing is kind of putting this back together, a little Humpty Dumpty style here. I know all of his parts that he needs to have in the end. I'm working backwards for them. Okay, and so that's how you build those larger, higher degree polynomials with those complex and imaginary solutions. Okay, last couple questions here. Solve the quadratic equation, x squared plus 9 equals 0. What are the x-intercepts of the graph? Okay, so first of all, if you tried to solve this algebraically, you'd subtract the 9, take the square root, and you'd get plus or minus 3i as your solutions. Again, notice how I'm using the word solutions. These are not x-intercepts. Imaginary solutions are not going to cross the x-axis. So when it asks you what are the x-intercepts, there aren't any. There are solutions, but there are not x-intercepts. And this makes sense. If you were to actually graph x squared plus 9, based on our prior knowledge, even from Algebra 1, you would know that this is a happy parabola that's been shifted up 9 units. That is not crossing the x-axis. So this is why my algebraic solution makes sense. It has solutions, plus or minus 3i, but it does not have x-intercepts, because there are no real solutions. All right, last question. Find the solutions to that blah, 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 fifth degree polynomial. What are the x-intercepts of the graph of the function? Okay, so first thing I'm noticing here is that I have a GCF of x that I can pull out. Okay, what else can I do? I think because there's a leading coefficient of 2, and I'm noticing it goes x to the 4th x squared, that I can factor this like an adds multiplies trinomial, just with a higher power. So what I'm going to do is do the triangle. So I've got 2 times negative 3, which is negative 6. So I'm looking for factors of negative 6 that sum to negative 5. So negative 6 and 1. And I'm going to rewrite that inner part. Okay. Notice how I kept these as x squareds now because I'm splitting up the negative 5x squared part. Out of the first 2, I can pull out a 2x squared. And out of the next 2, I can pull out a 1. This is looking promising. Alright, so this factors 2x. He's still hanging out here. 2x squared plus 1, x squared minus 3. That was a fun little triangle factoring in there. Okay, so at this point, I'm going to set each of the parts equal to 0. So, kind of running out of room here, is what it is. If I have x in front, that just means x equals 0. Okay, then I have 2x squared plus 1 equals 0. So if I solve this, I'd subtract the 1, divide by 2, and take the square root. Okay, I know the negative is going to come out as an I. And while I'm at it, I'm going to rationalize that to radical 2 over 2, because I'd have to multiply the top and bottom by radical 2 anyway. So just so you guys know, in my head, I'm kind of rationalizing as I go. So out of this portion right here, I got 2 solutions, which makes sense to me, based on the power of 2. And they were both imaginary, plus or minus I radical 2 over 2. Okay, and lastly, I had x squared minus 3 equals 0. So that gives me 2 more solutions, plus or minus the square root of 3. All right, let me highlight these. Okay, so my solutions, I got x equals 0, x equals plus or minus I radical 2 over 2, and plus or minus the square root of 3. Okay, those are my solutions. Let's see, how many do I have? I have 1, 2, 3, 4, 5. Look at the original degree of my function. What is it? Oh my god, it's degree 5! So this is actually leading us into what we'll talk about when we come back from our Thanksgiving break, is the fundamental theorem of algebra, which really says that you will have as many solutions as you do the power of the polynomial that you are looking at. So, degree 5 polynomial, 5 solutions. Oh yeah, I should probably answer the original question. What are the x-intercepts of the graph? Oh snap. The x-intercepts are the ones that are real, correct? So the ones that are real are x equals 0 and x equals plus or minus radical 3. Wow, the green on the pink really turned black there. Okay. There you go. Write this out over here. X-intercepts are x equals 0 and x equals plus or minus radical 3. There you go. Alright, so that's the end of the notes. Hopefully you guys were good. Okay. Alright. See you when we come back from Thanksgiving. Bye!